Welcome to Ready to Derive. In this video, we learn to solve a specific type of differential equation using the method of separation of variables. We begin by learning to recognize a separable differential equation, and then we learn how to find both general and particular solutions to such equations. As always, we get lots of practice with pretty visuals and a real-life context problem to make what can be a very dry topic a little more engaging. So, without further ado, let's get started. So let's first distinguish between what is a separable differential equation, what isn't, by understanding the definition of one. It's one in which dy by dx can be expressed as a product of two functions, one of x and one of y. And implied in all this is that we're dealing with first-order differential equations. That's one in which only the first derivative appears, no higher-order derivatives. So here's an example. And why is this separable? Because it is possible to get all the y terms on one side of the equation, all the x terms on the other. So if we divide it by y minus 1 on both sides, that would be multiplying by 1 over y minus 1, we would get 1 over y minus 1, and now we do have dy there, and we're going to do something which seems kind of illegal, but is perfectly allowable, which is to multiply both sides by dx. In doing that, we get the x terms to one side and the y terms to the other. So now do not think of dy over dx as a fraction. I know it feels like we're kind of cross-multiplying here. They're representations, they're infinitesimals. So dy is an infinitesimal change in y, and so is dx, and this is how those changes are related. Now, we also can say it could also be written in this way, dy by dx, but as a quotient, but we have to understand that any quotient can also be written as the product. So it's really the same scenario as the one above, but it's good to be able to recognize it when it arises. So in this one, we can spot instantly that if we multiply both sides by e to the y and by dx, I'm not going to write that because you can sort of see that easily enough, we get e to the y dy equals cosine x dx. And similarly, that quotient can be written in this form. So it's just g of y times 1 over f of x. It's still a product in disguise. So we have a situation like this. And if we multiply both sides, now this is interesting. We don't want to multiply rad x on both sides. We want to leave rad x over there because we know the dx is going to cross over. So we are going to actually have to multiply by 1 over ln y and multiply over by dx, and we would get 1 over ln y dy equals 1 over radical x dx. So these are all examples of separable differential equations. So here's a little more practice determining if a differential equation is separable. Sometimes you have to do a little algebraic manipulation to determine it. So here's one. Instead of seeing dy by dx, we see y prime, but it's better to write it as dy by dx. And we see that dy by dx is common to both these terms. So we know we only want it to appear once, so we could begin by factoring it out, and I'll write it as dy by dx instead. And then we have x plus 1 left behind equals y. And then if I get dy by dx alone by dividing both sides by x plus 1, I have a quotient. I've written dy by dx as a quotient, and I know if I separate the variables, so bring y to the left side, the y terms, leave the x term on the right side, and multiply by dx, so to speak, this is indeed a separable equation. Now, what about this one, dy by dx plus x equals y? So first of all, let's get dy by dx alone. So we're going to subtract x from both sides, and there we see already that we do not have a function of y times a function of x. We actually have a difference. And you may say, well, let's multiply up by dx and see what happens. So let's try that. So if we multiplied up by dx, well, unfortunately we can't release that y term from there. So there's no way of getting y to the other side, to the left side, without it dx being attached to it. So this is not a separable equation. Now what about this one here? It doesn't look like a function of y times the function of x unless we use our rules of exponents and write it like this. And then we can see that actually if we divide both sides by e to the y, so 1 over e to the y dy equals e to the minus x dx. And actually, it's a nice symmetric equation because if we rewrite that, we have this. Definitely separable. And finally, what about this? There's no, x isn't even present in this. But this is not a problem because the function of x could be something like over 1. So we can separate this as 1 over y dy equals 1 dx, and this is still considered a separable equation. Now, just to give you, you might say, well, what if no y is in there? What if it's just x? So what if it was like this? This is also a differential equation, but this is an easy one to find the answer to because the variables match. So if the variables match, then dy by dx is equal to x. That's really just finding the antiderivative of x, which would be half x squared plus c. So you can see that the whole point of differential equations is dealing with the presence of y in the differential equation. X will appear as well, but doesn't have to appear. But yeah, so this is technically a differential equation, but it's a very simple one that we do not need these methods to solve. So now we get to practice solving a differential equation thanks to this method of separation of variables. So here's our first differential equation example, and we are going to begin by separating those variables. So we will get y dy equals x dx. Not too much explanation here because we practiced it already. And then the second step will be to integrate both sides with respect to each variable. So I can just kind of stick an integration sign on both sides because you can do anything you like to both sides of the equation. I could have taken the log of both sides of the equation or taken the square root of both sides. So this is perfectly legal. And what this is asking us to do is to find the antiderivative of each side. So the antiderivative of y with respect to that variable would just be a half y squared plus a constant. And on the other side, similarly, half x squared plus, let's see, there's sort of another constant. So maybe if I call that C1 and C2, because they're probably different values depending on the scenario. But a technique here is to realize that, well, if I just subtract C1 from both sides and do C2 minus C1, I really just create another constant. And it doesn't matter what it's called. So I'm just going to call it C. So the individual C1 and C2 don't matter because they'd eventually merge to form a new constant. Let's call it C. Similarly, I the next step is to solve for y. So I am going to multiply both sides by 2, and I'm going to get y squared equals x squared. And you might say that I should put 2c there, but once again, 2c is just another constant. We kind of can absorb that, and we'll just call it c. And then finally, to get y alone, we would take the square root of both sides, x squared plus c. And let's not forget, though, we do need a plus minus in front of there to allow for a negative square root. So this is our general solution to this differential equation. And on the next slide, we'll start to look at particular solutions that go through specified points. So we're going to continue with the same example and practice finding particular solutions to differential equations. So the general solution to this differential equation is, notice it has a c in it, a constant that's unknown. Particular solutions are going to allow us to actually find that value of c. It's almost like plugging a point into equation slope-intercept form to find the constant, which is the y-intercept, kind of the same idea. So let's start with, let's pretend that we know that f of -1 is equal to 2, which is the same as saying the point -1, 2 is needs to be on the solution curve. So what will be the equation of the solution curve that goes through that? Well, you just plug in. So y is 2 and x, now 2 is a positive number, so I don't really need that negative in front of the radical if I know the output has to be positive. So I can plug in -1 for x plus c, and then I can solve. So I would get 2 equals square root of 1 plus c, so I can square both sides. 1 plus c, and then that would give me c equals 3. So my particular solution then, knowing that it has to pass through a positive y value, would be this. And just to practice one more time, if we have f of 3 equals -2, by the same reasoning, we would plug in -2 for y. And notice now that we have where y is negative, so technically we are looking at the negative version of this, 3 squared plus c. If we square both sides, we get 4 equals, well, 3 squared is 9 plus c, which gives c equals -5. And our equation then is y equals our particular solution, x squared minus 5. So let's look at these visually because it's kind of pleasing to do so. Here's a slope field for that differential equation. And when we wanted to pass through, let's see, let me get this here. So the first, for part A, we needed to pass through the point -1, 2. So this, oops, let me get a different, this particular solution matches the green graph. And for the second one, f of 3 is -2. This is right here. F of 3 is -2. So this equation matches the red graph. And we found 2 examples of particular solutions. And as you can, in slope fields, we learned that depending on the initial condition, the family of curves would vary. And so we locked in particular curves depending on the initial condition. So here's another practice problem, a new differential equation with a new initial condition. So the first step is to separate the variables, and I would recommend leaving the 1/3 or any constants on the right-hand side with the x terms, because often the y side is the more difficult one to take the antiderivative of. So, and what you realize is you've got y minus 2 squared here, so you will obviously want to divide y minus 2 squared on both sides, which is the same as multiplying by 1 minus 2 squared. 1 over, sorry, y minus 2 squared on both sides. So sometimes people will, kind of separate the variables and write something like this, which is true as well, but it's important to be able to break that up, as we'll do in the next step. So when we want to take the integral of both sides, it's 1 over y minus 2 squared, which you realize is it's better to get it as a negative exponent, so we can use the reverse power rule. And on the other side, I would even bring that constant outside the integral sign, which is allowable, just to simplify the process. So the antiderivative of the left side, so this, you might do this using u substitution, or you can kind of do it by inspection. You realize that you have to add 1 to the exponent, and then you would have to compensate for that by putting a negative in front, because the derivative of y minus 2 to the -1 would be -1 times y minus 2 to the -2. So these negatives here would cancel out, this and this, when you take the derivative, and get you back to what we started with. So, and then on the right-hand side, the antiderivative of x is 1/2 x squared. And let's not forget that kind of joint constant there. And then the next step is going to be substitute and solve for c. And I don't particularly enjoy substituting when I'm dealing with negative exponents. So I might just rewrite the left-hand side as this first, and then simplify. Let's just simplify that a little. And then we get to solve for c, which is to plug in the point 1, 0 based on this initial condition up here. So when we plug that in, we get -1 over 0 minus 2 equals 1/6 of 1 squared plus c. That gives 1/2 equals 1/6 plus c. And this gives a constant of 1/3. And we'll proceed on to the next slide to finish solving for y. So here is the solution equation, the particular solution with the value of c replaced with 1/3. And then our last step is to solve for y. Now notice that y is in the denominator on the left-hand side. So that's going to be hard to kind of work with until we get a fraction on the right-hand side, a single on the fraction on the right-hand side. So let's just do that. Let's just get a common denominator on the right, which is 6, and then we would get x squared plus that would be 2 over 6, right? If we multiply this by 2 over 2. Now at this stage, you could cross multiply because you have a proportion. You have to cross multiply and then divide through again to get y alone and x onto the other side. Or you could take the reciprocal of both sides, which is perfectly legal. As an example, up here, if I told you that 1/2 equals, I don't know, 3/6, well, the reciprocal of that is true as well. 2 over 1 would equal 6 over 3. So that's all we're going to do right now. So we'll get y minus 2 over -1 equals 6 over x squared plus 2. Let's, at this point, let's get rid of that -1 underneath the y minus 2 by multiplying over. We'll put that with the 6 for the time being. And then all we have to do is add 2 to both sides. So we get y equals -6 over x squared plus 2 as our solution, as our particular solution. And we could check again. Remember, it was supposed to go through the point 1, 0. And if we plug 0 in for y and 1 in for x, we would get 3 on the bottom here. This would become -2. -2 plus 2 is 0, and it works. So just as a recap, this was the differential equation we began with. And we were asked to find a particular solution through the point 1, 0. And here I graphed this equation here. And as you can see, it fits the slope field perfectly. So in our third practice problem, we're going to find a couple of particular solutions to a differential equation given 2 different initial conditions. So the first step, as we know, is to separate the variables, divide both sides by e to the y, and leave cosine x where it is, bring dx to the other side. Second step is to integrate, and don't forget the plus c. Now when I do this, I'm going to transform the left-hand side to this, because we don't have an integral rule for quotients. So we have to get it written like that. And then we have cosine x dx here. The antiderivative of e to the minus y would be e to the minus y with a negative in front to compensate for that negative in the exponent. If you have any doubt as to why that works, do this by u substitution by letting u equal -y, and you will get the same result. And the antiderivative of cosine x is sine x plus c. Don't forget the c, otherwise you will lose a lot of credit on this problem if this was on the AP exam from this point on. For the third step, we're going to switch them around. This time we're going to solve for y first and get a general solution, and then we can plug in the particular, the initial conditions to get the particular solutions. And I'm going to just sort of bring the negative to the other side and get negative sine x plus c times -1 would just be a new constant, so we'll just call it plus c again. Okay, it's still a constant. And then the way to solve both sides when you have e raised to something is to do the inverse, which is to take the ln of both sides. And we can do that on the left side. The ln, e, they undo each other. You're left with -y equals ln. I'm just going to rearrange this as c minus sine x. And then we just multiply both sides by -1. We get this. So this is our general solution. And then in the next slide, we're going to just plug in our different initial conditions and solve for c, and then get our particular solutions. So here's the general solution from the slide before. And notice since it's solved for y, it makes it easier to plug in different initial conditions. That's why we switched the steps and didn't leave solving for y for the last step. So we just get to plug in here. So 0 equals negative ln c minus sine 0. Sine of 0 is 0. We get 0 equals negative ln c, which is the same as this. And that means that c must equal 1, because the log to any base of 1 is always 0. And that gives that this particular solution through this point is given by that. And now we repeat, but this time we plug in negative 1 equals negative ln c, because sine of 0 is still 0, which is the same as this. And we know then that c must be e, because the ln of e is 1. And this gives us that y, this particular solution, we'll plug in e for c, is this. And just to recap, this was our differential equation. And this is a slope field of it with the actual particular solutions drawn in. So this here matches the purple graph because it had to go through the point 0, 0, which is right there. And this one here matches the green graph, this particular solution, because it had to go through the point 0, negative 1. So for the last example, we're going to revisit a contextual application of differential equations that I introduced in the very first video in this unit, Introduction to Differential Equations. And this is a kind of models a real life scenario. The rate at which a population is growing is always going to be proportional to the size of the population without any limiting constraints. That is, so in this case, it seems that the rate is 1/10 of the population at the size. So it kind of makes sense. The bigger the population, the faster it's going to grow. The smaller the population, the slower it's going to grow. And our initial condition is P of 0 equals 1500, which means that the initial population size was 1500. Now, we're not using y's and x's anymore, but it's important to realize that, so P is our y, is the new y, and T is the new x. So we're going to do this without me prompting the steps. Let's see if we can do this kind of organically. So we are going to start with the first step, which is, so I'm not going to write the steps out, but I am going to say them. The first step is to separate the variables. So I'll bring the p to this side and leave the constant up there and bring dt over. And then we're going to take the antiderivative, and the antiderivative of 1 over anything is the ln of the absolute value of that. The antiderivative of 0.1 is just 0.1 times the variable, and let's not forget the c. And then we get to use the initial condition to solve for c. And if we plug this in, we get ln of 1500. We don't really need the absolute value there because it's already positive. Is 0.1 times 0 plus c. So c equals ln 1500. And before you get your calculator out, just leave it like that because an interesting thing is going to happen to that term. So let's see, we are back up here now, and let's just put c back in. So ln, and I'm going to remove the absolute value from the p because we're dealing with population here, which is positive, and we get 0.1 t plus ln 1500. And now what we're going to do to kind of solve an ln equation or logarithm equation, we're going to just raise both sides to the power of e, because e and ln will undo each other, they're inverse functions, and we're left with p equals e to the 0.1 t plus ln 1500. Now, according to rules of exponents, we can split this up. Now it's not plus, it's times. So the e raised to a plus b is e to the a times e to the b. We get this ln 1500, which of course is very nice because this works out e to the ln, they undo each other, and we get left with 1500, which I'm going to move to the front here. 0.1t, and I'll just call this p of t because we realize p is a function of t. And so this is our particular solution to this differential equation, this model, and you might make some comparisons. You probably saw this in pre-calculus, like it's an exponential growth model, so the amount at any time t is equal to the initial amount times e to the kt, and you might recall having solved for k with given sort of particular conditions, initial conditions. So, and this k is the 0.1 here. And so this is something we've met before, but now we actually generate it by solving a differential equation. And that brings us to the end of this lesson. I hope you found it helpful. And if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.